You know, every single day we use these incredibly powerful machines with just a simple click of a button. But have you ever stopped to wonder what's really going on inside that box? Today, we're going to pull back the curtain and demystify the most fundamental process in all of tech, how a computer actually computes. It seems so simple, doesn't it? You click an icon, a program opens. But that one little click sets off this insane, super fast journey inside your machine. We're going to follow a single command on its adventure, from your fingertip all the way to the final calculation. Okay, so the very first thing we need to wrap our heads around is this really simple but kind of mind-blowing idea. To a computer, the instructions that tell it what to do and the data it works with, well, they're the exact same thing. Yeah, this whole idea is called the stored program concept, and it is, no joke, the foundation of all modern computing. It means a computer isn't just a fancy calculator locked into doing one thing. Because its instructions are stored in memory just like any other piece of data, they can be changed, loaded, and replaced on the fly. This is what makes your computer a truly general-purpose, do-anything machine. So what exactly is an instruction? Well, it's not some complex sentence like, open my web browser. Down at the middle, it's literally just a string of ones and zeros, a binary code. And each unique code tells the computer to do one tiny, specific task, like add this number, move that piece of data, or compare these two things. All right, so how do we get from code that people like us can actually read to the simple ones and zeros the machine needs? Well, it's all about translation. So you can imagine, programmers aren't sitting there typing out ones and zeros all day. That would be a nightmare. Instead, they use a symbolic language called assembly, with short commands like LDA for load A. Then, a special program called an assembler acts like a translator, converting these human-readable symbols into the pure binary machine code that the hardware actually understands. And take a look at this table. It shows you exactly what I'm talking about. A simple, almost English command like LDAA gets translated by the assembler into a very specific pattern of bits. Every single one of those assembly instructions has its own unique binary fingerprint. This is the language the computer speaks fluently. Okay, so picture this. Our instruction, now just a string of binary, is sitting there in the computer's memory, waiting for its big moment. The very first step on its journey is for the computer to go and grab it. All right, to help us keep track of this journey, we're going to use this simple little map of a computer's main parts. And our first stop, right here, in the memory block, which you probably know as RAM. The easiest way to think about RAM is like a huge wall of mailboxes. Every single mailbox, or cell, has its own unique address. Now, to find our instruction, the computer doesn't have to check them one by one. It uses that specific address to jump directly to the right spot. That's why we call it random access memory. It's incredibly efficient. Okay, so our instruction has been picked up from memory. Now it's time to head to the real brain of the whole operation, the central processing unit, or the CPU. So our little binary instruction hops on what's called a bus. You can think of it like an information superhighway inside the computer, and it travels from memory straight to its destination, the now highlighted CPU. Once it gets inside the CPU, our instruction meets two key players. First up is the control unit. This thing is basically the traffic cop. It looks at the instruction's binary code and figures out what needs to be done, then directs all the data to the right places. And then you've got the ALU, the arithmetic logic unit. This is the master calculator, the part that actually does all the math and logical comparisons. Now, the CPU also has this little secret weapon, its own super fast memory called registers. These are tiny storage spots right on the chip itself. Think of them as the CPU's personal scratch pad. They hold the current instruction and the data it's working on, so the ALU can access everything it needs instantly without having to go all the way back to RAM. Okay, so let's just quickly recap where we are. Our instruction has been grabbed from memory, the control unit has figured out what it means, and the data it needs is waiting in the registers. Now it is finally time for the ALU to do its thing. What we've just described is the fundamental rhythm of every computer. It's called the instruction cycle. Fetch the instruction from memory, decode it in the control unit, execute it in the ALU. That simple little three-step dance is the basis for everything, and it happens at a completely mind-boggling speed. Okay, let's make this super concrete. Let's say our instruction is just to add two numbers. The control unit points to the first number, or operand, and sends it to the ALU. Here it is, 0011 in binary, which we know as the number 3.
Then the second number pops in, also from a register. It's binary 0101, which is, of course, the number 5. So now the ALU has both of its inputs, and it's ready to go.
The ALU does its magic, the circuits flip, and boom, the result pops out, 1000, which is the binary for 8. The journey is complete. That result gets stored in another register, ready to be used by the very next instruction in the program. So yeah, we have only been following one tiny little instruction this whole time. But here's the crazy part. This exact same journey, fetch, decode, execute, is the foundation for absolutely everything your computer does, no matter how complicated it seems on the surface. Think about it. Playing a game, watching a video, even just scrolling on a web page. It all just boils down to millions or even billions of these tiny instructions, each one taking its own little journey through the CPU, all happening in a breathtakingly fast sequence. And it's pretty interesting because not all processors handle this the same way. There are basically two big schools of thought. CISC processors try to pack more power into a single instruction. On the other hand, RISC processors do the opposite. They use a much smaller set of super simple, super fast instructions. It's like asking, do you want one powerful tool that does a lot, or a whole bunch of simple, specialized tools that are incredibly fast? Both are just different ways to optimize that core, fetch, decode, execute cycle. So the next time you click that mouse or tap that screen, just take a second to remember the incredible journey you just set in motion. Billions of these tiny, elegant cycles happening every single second, translating your simple action into everything you see and do on your computer. It really isn't magic. It's just the beautiful dance of fetch, decode, and execute.